Okay. So the last time we looked at that function. That what? Let's go back to it real quick. Right? What's going to happen? Well, first of all, if you're thinking for a moment, well, hold on. You can't call a method from within inside itself. You're wrong. You absolutely can't. There's no rule against that. Don't make up new rules. And that's an important concept for what we're about to talk about. But what's going to happen here? Follow the rules you're already aware of. There's nothing special. There's nothing weird or new taking place here. What's going to happen? I call Line 2 says print out we. Line 3 says call So what does that mean? Well, we create a new call frame. One sec. For run line 2, print we, call create a new call frame for the call. So we keep making all these call frames and executing them, and each one calls another one. For every call to it calls and it's never going to end. This is going to go on forever. But unlike an infinite loop, I mean, this is theoretically an infinite loop, but there is a constraint that your computer has. Your call stack, your computer or the JVM, depending on your programming language or how it's set up, has a limit on how big that call stack is allowed to get. You're only allowed to go so deep into subsequent method calls. In typical programming, where you're not doing something like this, you're never going to go that deep on the stack. Usually. But once you start doing something like this, we've got an issue. That stack is just going to grow forever. But your computer has a hard limit. And when you see that hard limit, you see a stack overflow. That's what this is called. The stack overflowed. It had a hard limit, and it tried to grow beyond that. Now there's an interesting thing to observe here. The method How is that method defined? Well, this is what it says. Prints out we, and then calls Meaning, the method the definition of that method, which is this, what's written right here, the definition includes itself. The definition of includes a call to which is a little funny though. But there's nothing wrong with this. There's no rules being broken. So, how many people are in that line? Someone answer. People are the little orange stick figures.
15.
How? How do you know?
I counted.
You counted. Tell me how you counted.
I looked at each stick figure individually and then sorted them in my head.
So you went 1, 2, 3, 4, 5, 6, 7, 8. Is that what you did? Yeah. Who here did that? Yeah. Oh, sorry. You had a question.
No, you asked what happens if this runs.
Ah.
I didn't take that as the rhetorical question.
Pardon me. You're working too hard. Whoever pointed and went 1, 2, 3, 4, you're working way too hard. No. Here is how I would answer that question. I'm going to say, no, okay. The number of people in that line of people there is exactly 1 plus the number of people after that first person. That's what I see. But then this, of course, begs the question, well, hold on. You just said it's 1 plus the number of people after the first person. That's not a valid answer. You just answered that question with another question. Because the question then comes, well, how many people are after that first person? But an interesting thing here is I'm asking the same question on a slightly different scenario, in a slightly different way. So the number of people in this row is 1 plus the number of people after the first person. So I'm asking the same question. How many people are in this set of people? But the set of people is different the second time I asked it. So we got a nice good long row of people right there, starting with you, Sky. 1, 2, 3, 4, 5. Okay, cool. So I'm going to ask you, how many people, I'm pointing at you, so you better pay attention. I'm going to ask you, how many people are in that row of people? Okay? And here's what you're going to say. You're going to say it's 1 plus the number of people after you, after being that way. But you don't know the number of people, you don't know how many people are after you. You don't know. But you do know that if you did know, it's going to be, so let's say it's X, for example. If it's X people after you, how many people are there in total, including you?
X plus 1.
X plus 1. Great. So what you got to do is you got to find a way to figure out how many people are after you. So you can find out what that X is. And here's how you're going to do it. You're going to ask him, how many people are there after you? Okay, so ask him.
How many people are there after you?
So here's what you got to do. He asked you a question. And the question is, how many people are there in this row, including you? And the answer to that is, well, you, 1, plus the number of people after you. Right? How many people are after you? Well, you don't know. But you can find out. How do you find out? You're going to ask him. So now you need to answer. How many people are there in that row? We're not worried about them two. We're always worried about there.
Have to ask her.
You got to ask her. So how many people are there? How many people are there? Now, we're in a funny situation. We're at the end. So the answer, you've got a little bit of a different situation. Because I ask you, how many people are there in that row following you? And the answer is you plus the number of people after you. But you happen to know how many people are after you? 0. And you just happen to know that because, well, there's nothing left. So he can answer the question of how many people are there? 1. So you tell him 1. So if there's 1 people after you, how many are there in total, including you? 2. So you can tell her. If there's 2 people, how many are there, including you? If there's 3 people, how many are there, including you? 6. In order for you to answer your question, they needed to answer their question. In order for you to answer your question, they had to answer. And then them, and then them, and then them. Once you answered, you could answer. And then you could answer, and then you could answer, you could answer, you could answer. We kind of started here, went down, and back up. It's a little weird though, right? But the value, the awesomeness of this is we answered that question by asking a ridiculously simple question with a ridiculously simple answer. 1 plus the number of people after you. The problem was that how many people are after you is kind of a big mystery. But you answered that question by asking the exact same simple question with the exact same simple answer, just with different values because the context changed. So we asked the same question multiple times, but each question was stupid simple, with a stupid simple answer. So let's take a step back. I could define a group of people iteratively. Very simple. A group of people is 2 people, They have to have more than one person. Okay? So a group of people is 2 people, or 3 people, or 4 people, or so on and so on and so on. And I can do this forever. I can do this until the end of time. Just keep adding whatever. But I could define it in a different way. We can define something in terms of itself, which, as humans, we might naturally have an aversion to, but the reality is nature really likes this, actually. The root of all of this is recursion. When something is defined in terms of itself, we have a recursive definition. Does someone do me a favor and Google recursion? Real quick. Yeah.
I can take a guess. Is a method that calls itself until conditions satisfied?
Yeah, well, that's what it is, but someone Google recursion.
A repeated application of recursive procedure.
Well, let's see. Well, no, actually, I need to answer recursion first. And then, oh. Look at that, Google made a good joke. Has anyone ever seen this one? How obnoxious is that?
Do a barrel roll one of the tail?
Oh, maybe. Let's see.
I do remember that, yeah.
For everyone, if you look at the maps, it gives you.
Oh my God. all right. So, we're going to define a group of people in terms of itself. And what you'll notice is that definition tends to be very succinct. And succinct is just a fancy way of saying like nice, clean, small, tight, nice, succinct. So a group of people is either 2 people or a group of people plus one more person. Okay? So with this definition, we have now described all possible groups of people in terms of quantities. But there's like a big X there, right? Because it's like, well, we need to know the thing we have is a group of people plus one more in order to conclude it's a group of people. So if I give you one person, would you conclude that this is a group of people? Okay. If I gave you 2 people, could you conclude if 2 people is a group of people? Yes. How? It literally says right there, by the definition of a group of people, it's 2 people. So it is by definition. Why? Because it's written there and that is the way it is. Now if I ask you if 3 people is a group of people, is it?
True.
True. Why?
Because 2 people plus 1 more people is 3 people.
Okay, because 2 people is a group of people. Why? Well, it says so right there. And then if I have a group of people, 2 people, and I add one more, that's 3 people, by the second thing, that's a group of people. If I gave you 7, if I add, 5, is 5 people a group of people? I know you're going to say, yeah, we know. But let's break this down. You're thinking too much like a human, we got to be dumb. In order to know if 5 people is a group of people, what must we know first? This isn't a trick question. No. We're not there yet. Because I don't have 2 people. I got 5 people. So what were you going to say?
Is 4 a group of people?
We got to know 4 is a group of people. Because 4 plus 1 is 5. So I can only conclude that 5 is a group of people if I know that 4 is a group of people. If 4 is not a group of people, 5 is not a group of people. But if 4 is, 5 is. So we have to answer the question, is 4 people a group of people? So, is 4 people a group of people? In order to answer that question, what must I know? if 3 people are a group of people. Because if 3 is, 4 is. And if 4 is, 5 is. So is 3 people a group of people? Do we know? How do we know?
Because 2 is a group of people.
Because, well, we can conclude that 3 is a group of people if we know if 3 minus 1, 2 is a group of people. But it is. Because it says so right there. Which means 3 is, which means 4 is, which means 5 is. You'll notice that we can actually, there's 2 ways we could approach stuff like this. We could start from the bottom, 2, and just go up forever. Or we could start at some arbitrary point and work our way down, and then back up. It's kind of like a directionality there. But at the end of the day, we can answer all questions. All right. This is just working through what we just did. So, there are 2 parts of your typical recursive definition of things. I will say, technically, it only needs 1 part. Technically, chances are you really want 2 parts. Okay, just to be fair. So technically, the uh-oh example didn't have what we call a base case. A base case is some like concrete starting point / stopping point. The 2 people. A hard, fast rule. Well defined, 2 people is a group of people, that's our base case. The other thing we have is the recursive case. The case where we have the definition of the thing that's defined in terms of itself. That is a group of people plus 1 more person is a group of people. So there's a hard answer, that's the base case, and then the recursive case, which is the thing that calls itself. Now, I'm going to talk about recursion in a simple way. Now, when I say simple, I don't mean trivial. I mean, we could make this more complex. You can have a co-recursion where one function calls another function that calls the original, and we're not going to touch that right now. It's too complex for the sake of what we're doing. Now, technically, to have something that's recursive, you don't need a base case. But 99.999% of the time, you'll want a base case. Because if you don't, you end up running into things like what happens with uh-oh. There was no base case in uh-oh. There was no stopping point. It just ran forever until it crashed the computer. Now, mind you, in a purely theoretical way, like mathematically theoretical, these recursive definitions, like that function, that uh-oh function, I know you look at that and you go, it's a computer program, but really it's just the definition of something that's in the form of a program that you're familiar with in Java. But the idea is programming computer agnostic. It doesn't care that it's in Java or whatnot. That idea of uh-oh calling itself doesn't have to be in the computer. It's more like a formal mathematical definition of something. And in reality, the only reason the recursive uh-oh broke was because of the limitations of those computers and how they were designed. You could design any other computational system, and you could design other computational systems that aren't designed that way, and recursion will never stop. It will just be an infinite loop that will never stop. But as a consequence of how these are designed, yeah, it crashes the program. But that is not a fundamental truth of the universe, that it's going to crash the program. No, that's just a consequence of these computing machines that we use. In a purely formal way, it's like that would run forever. Now, things could be defined recursively, not just algorithms, but data structures. We could define a data structure, something like a simple list. Think back to Python, a list. We could define a list recursively really easily. And a list is a data structure, not an algorithm, though, you use algorithms to define the data structure, but let's take a moment and think. The base case is an empty list is a list. Okay? If you have a list, but there's nothing in it, it's still a list. All right? The recursive case is there is a head of a list followed by the tail of the list, where the tail is just the remaining portion of a list. So, if I give you this list right here, A, B, C, D, E, there's a list. And the question then gets posed, is that a list? I know I just said it was, but here's something. Is this a list? Well, it looks like a list, but let's go answer. By following the recursive definition, we need to be able to get the header of a list and have the tail of a list. And that tail of a list must be a list in order for the whole thing to be a list. So I can take the head of the list, which is A, followed by the rest of the list, which is B, C, D, and E. So I've got a head and a tail. We could break that tail down by taking the head out of this list, which is B. And then the head out of that list, which is C. The head out of that list, which is D. The head out of that list, which is E. But now we have an empty list. There's no head anymore. But does it matter? No. Because what do I know about an empty list? It's a list. There's a recursive definition of a list. You'll notice repeating patterns. Now, a couple things I want to hit before I go further. Who here, raise your hand and be honest, who here has heard of recursion before? Before we talked about it, you've heard about recursion. Great. Often, a lot of new programmers like to talk about, oh, recursion, that's going to mess you up. It's so hard. It's where things got hard. That's where it fell off. That's nonsense. And those tend to be programmers who are just terrible people. Recursion is not intrinsically harder to understand than iterative. There are some programming languages out there where there's no such thing as a loop. There's no such thing as a for loop or a while loop. No such thing. If you want to do anything with like looping, it's all recursion. I spent a year of my life using those types of programming languages, and then when I went back to like using something like Java, I actually had a really hard time figuring out how to use loops again. Which sounds silly, but it's true. The point of this is, it's not that recursion is hard, it's that it's a little different. It requires a little bit of a flip in your brain. It's not trivial in a way that loops are not trivial. But if you're stepping into this thinking, oh, this is too complex, I'll never understand it, you're setting yourself up for failure, and it's absolutely not true. It's not. Just take our time. There's no trick here. If you find it overly complex, you're doing it to yourself. You're making it more complicated than it is. What are the rules that we've been following up until now? Everything that we're talking about is going to be using, especially when we look at the code, it's going to be using nothing new. We're going to be using everything we've been doing before in maybe a slightly different way, but all the same rules apply. And iterative processes in nature, there's no for loop in nature. Iterative processes in nature tend to follow recursion in terms of repeating the same thing, the same stupid little function, over and over and over and over again. You've got these little functions that are like things, these repeating patterns pop up a lot. Okay. In the counting example, it may feel like cheating by saying 1 plus however many things are after the front. However many things follow. However many things after the front seems like skipping a step, right? But it isn't. Because we're going to answer that question. The 1 plus however many things after the front, that question is going to get answered. We can't answer the whole question until that sub-question is answered. But like I said moments ago, that sub-question is the exact same question that was just asked. The only difference is it was asked on like a slightly smaller version of the problem. It wasn't a list of 15, it was a list of 14 things that it was asked on. And then that list of 14 is going to ask the exact same question of a list of size of 13. And so on and so on and so on. It's not cheating, it's delegating. I'm going to answer this question once this person answers that question. That's what happened there. You delegated the work of counting out how many things are all there by asking him. Who asked him? Who asked her? Who asked him? Who asked him? It's just delegating. It's just breaking the problem down further and further and further, but the code is like explicitly breaking the problem down. We have these repeating patterns. Yeah. So we kept going down until we got to empty. With the empty list, we kept going down until we got to an empty list. With the group of people, we kept going down until we hit that hard base case of, well, 2 people is a group of people. Why? Because it says. Now, it's going up and going down. The set of natural numbers can be defined recursively as 0 is a natural number. Okay? You don't believe me? Tough. It is. Why? Because I said so right there. And then, a natural number plus 1 is a natural number. All right? So 0 is a natural number. And natural numbers are like 0, 1, 2, 3, 4, 5, right? In case you forgot. If 0 is a natural number, and any natural number plus 1 is a natural number. That's a recursive definition. Now, we could go about this 2 ways, like I just talked about a moment ago. This right here provides a complete definition of all natural numbers possible. You could ask me any number, and we could answer whether or not it's a natural number or not with this right here, these 2 little lines. Really simple. It's nice. Now, we could start at the base case and generate all possible natural numbers. 0 is a natural number, which means 0 plus 1 is a natural number because 0 is a natural number. Means 2 is a natural number because we just concluded that 1 was a natural number. Means 3 is a natural number because we just concluded that 2 is a natural number, and so on. That's kind of like going up. Or we could go down by starting with some arbitrary number and work our way down to the base case. Is 5 a natural number? Well, I don't know. It's 3? Because if 3 is, 5, sorry. It's 4. Because if 4 is, 5 is. And then if 3 is, 4 is, and so on. So there's kind of like this directionality, but the directionality is kind of arbitrary, and it really just kind of depends on what question we're asking. The underlying concepts are the same. If you're looking for, like, how do I know if I go up or down? You're thinking about it wrong. You don't ask that question until you have the question you're trying to answer. Right? If I say generate all natural numbers, well, you start with the base case and go. If I say is x a natural number, well, you kind of work your way down. And then back up. Because you have function calls, right? So is 5 a natural number? Well, is 4, is 3, is 2, is 1, is 0? Yeah, okay, so yes, oh, yes, 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 right? Like we did there. We went down and then up. 1 plus the rest, 1 plus the rest, and so on. And you said 1, and then you said 2, 3, and so on. That's that down and up versus up and down, whatever. People tend to love recursion. Mathematicians tend to love recursion. Biologists tend to love recursion too for some weird reason. But computers don't. Because computers have a hard time, like I was saying a moment ago, about if I write a for loop and I tell you create a variable to count, let's think about what the computer has to do. The computer is going to have a for loop. It's going to have a variable, I'll call it C, starts at 0. Now if I have a for loop that runs to infinity, okay? And that for loop, all the body of that for loop does is adds 1 to that variable C. So every time that loop runs, the computer is going to have to go to that chunk of memory and go like, okay, well, that becomes a 1. Oh, okay, you ran it again, that becomes a 2. And so on and so on and so on. But, if we were to do this recursively, which we'll see examples of this later on how we would do this explicitly, but if we do this recursively, we just learned about this whole call frame thing. And the call frame has to set aside RAM for parameters. Let me put it this way. Let's say I had a function f of x, right? And the function, what it does is it's going to calculate f. I want to think of how I would do this a little clearer. Give me a moment. No, I can't define it with an equality like that. You know what? I'm not going to bother doing it this way anyways. It's going to just make it more complicated. These are terrible. Do I have my own? If I were to do this recursively, your computer needs to go make a call frame. And in it, it needs to know the variable, the current value of the variable, 0. And then it calls the recursive function, except it's just going to add 1 to it. And it's, right? So it's going to make another call frame, create another chunk for that variable, and have a 1. And then make another call frame, another chunk of RAM, or that 2. And then another call frame, 3. And it's going to have to do this, so that this runs for infinity. It's going to have to create all these call frames. That's a lot of work that the computer has to do. It's not even your program doing it. It's kind of like your computer having to go and allocate this memory and whatnot. Where if you do it iteratively, we're just updating this one variable. Computers tend to hate recursion. We like it. Computers don't. There was a question. Someone's, yes?
The call frames be the same if you use greater than and less than, comparing values?
The call frames are just for each subsequent recursive call. You're thinking too detailed of what the conditions are in there. Don't even think about that. Each subsequent recursive call has to make a new call frame with all the relevant variables. That's all we're going to worry about right now. All right. That was okay. So, who here has ever heard of factorial? Put up your hand. We talked about 161. Come on. Factorial. Here is the nice definition of factorial. Okay? We can think of it, maybe programmers like to think of it a little bit more like this. N factorial is n times n minus 1 times n minus 2 times n minus 3 times 3 times 2 times 1, although times 1 is kind of useless. Right? We can think of it like that. Or we could define it very, very succinctly, recursively. N factorial, if n is 0, n factorial is 1. Otherwise, if n is greater than 0, n factorial is n times n minus 1 factorial. So to know what n factorial is, I just have to multiply n by the factorial of n minus 1. And if that doesn't make sense, just look at it like this. Imagine, ignore it, only look at the 3, 2, 1. In order to know 3 factorial, I got to know what 2 factorial is, right? It's the same idea. Now, just as an FYI, just note that 0 factorial is 1. And you might think that's weird. There's a couple reasons for that. For the sake of now, just go with me. If you want to, why is it 1? Well, first and foremost, it is by definition. Why? Because we said so right there, in that definition right there. 2, well, 1 is the multiplicative identity. The identity for addition is 0, right? If I do x plus 0, what do you get back? X. Nothing changes. For multiplication, it's not 0. It's 1. Anything times 1 is itself, right? So that's why it's important here. It also aligns with something called the gamma functions, like with a more general thing of it. But anyways, let's think of like, what's 4 factorial? All right, well, 4 factorial, by that recursive definition, which if you forgot what it was, it's right this. It's either 1 if n is 0, or n times n minus 1 factorial. So if I ask you what's 4 factorial, n is 4. Which of these two apply? The first or the second one? Yeah. So that means 4 factorial is 4 times, what's n minus 1? What's 4 minus 1? 3. All right, so it's 4 times 3 factorial. Right? But we're not done, because I can't answer what 4 factorial is until I know the answer to 3 factorial. So let's go answer 3 factorial. All right, what's 3 factorial? Well, it's going to be that second case again, because 3 is greater than 0. So 3 factorial is just 3 times 3 minus 1, 2 factorial. What's 2 factorial? I don't know yet. 2 factorial is 2 times 1 factorial. What's 1 factorial? I don't know yet. So what's 1 factorial? Well, 1 factorial is 1 times 0 factorial. What's 0 factorial? I know what 0 factorial is. I don't need to ask any more questions. I can answer that question precisely. 0 factorial is 1. Why? It just is, because I said so. Because the definition said, when n is 0, it's 1. That's 1. So, 0 factorial is 1, which means 1 factorial, which was 1 times 0 factorial, is 1 times 1, which is 1. Which means I can now answer the previous question, which is what was 2 factorial? Well, 2 factorial was 2 times 1 factorial, and 1 factorial was just 1, so that means 2 times 1, which equals 2. So now I know what 2 factorial is. I can answer what 3 factorial is. 3 times 2 factorial, which means 3 times what 2 factorial was, which was 2, which means 6. And then lastly, 4 factorial is 4 times 3 factorial, which we just answered was 6, which is 24, right? This is a case of starting at 4 factorial, working down, and coming back up. Now, if I asked you what 5 factorial is right now, you know, I just asked what 3 factorial. How do I word this? The definition, the answer to what 5 factorial is.
120?
Well, yes. Not where I was going, but yes. Is, you know, I'll move on. I think I hit it a little harder later on. Let's put this in code. Here's an iterative version of factorial. Okay? Have a look at that code. Take a moment, look at it, understand it. Nothing in there should scare you, especially at this stage of the game. This iterative one clearly starts at the bottom and kind of works its way up. Yeah.
There's something I noticed. There might be a typo on the for loop. It says plus sign instead of plus.
It's not a typo, it's just I tried to, may have missed that lecture where we went on the discussion of plus plus I versus I plus plus. That's not a typo, it's perfectly fine, but I would actually like to change that for consistency. Classically speaking, very classically speaking, plus plus I is classically speaking faster. In practice, it's all nonsense and it doesn't matter. If someone actually wants to make a pull request to fix that, to change it to I++, by all means. All right, what was I saying? This here starts at the bottom and works its way up. And yeah, there you go. There's the iterative one. But look at the recursive one. Take a moment and look at that one. And I don't know about you, but there's like this, for lack of a better term, so both of these do the same thing in terms of, let's think of these like a black box. These two functions, we can think of them as a black box. Both of them are going to give identical answers to the same questions. So they're going to achieve the same thing, but they're going to do them a little differently. One's iterative, one's recursive. But there's something about that recursive one, for lack of a better term, that's just kind of like elegant. There's like a beauty to that recursive one. It's so simple. It's just, if n is 0, the answer is 1. If it's not, it's n times whatever the answer to the subproblem is. And it's that simple elegance that's, I don't know, there's something to it to me. There's nothing wrong with the iterative one, but now maybe you don't feel the same way, and if you don't, I'm going to say it's probably because you're just not that used to recursion. But having a little bit of experience, I can look at that iterative one, and I can look at that recursive one, and that recursive one is a lot simpler to me. It's a lot easier to understand. It's a lot easier to follow. And it's just, it's simple. It's nice. Any questions about those two? Yes?
Is the recursive function slower? It has to go down and back up.
So it's the reason it'll be. Okay, you've asked a remarkably complex. Sorry, that question has varying levels of complex answers. The quick answer is, I know what you're asking in terms of the number of steps, and yeah, I'm guessing the number of steps, I don't know, we'd have to sit down and like count the number of steps. Where the slowness comes is the creation of all those call frames, okay? Every time we do this hurts the computer. The computer is sluggish at this. It's not even what's happening like programmatically with what the code you wrote. It's just how the computer is doing its thing, right? There could be another system where maybe it's designed differently, and that won't be an issue. And then we have an interesting question on our hands. Now, and this is kind of like similar-ish to the idea of like the link structure in the arrays. Remember, well, the link structure, everything was constant time, right? With the inserts and removes, but with the array, it could be complicated. We might have to expand capacities, all this extra work, but in practice, arrays are way faster just by the nature of how they're built versus link structure. But that's a consequence of the computers, not natural truths about these mathematical ideas and formulations. Same thing with like the recursion. Now, in practice, many, I don't know how many, I don't know which ones or which, because there are some that I thought did that don't. One thing Java is remarkably good at is what they call tail end recursion optimization. Let me take a step back. Who here would say computer programs, well, that's like, your code is for a computer, right? When you write code for a computer, you're wrong. You're absolutely wrong. That nothing could be further from the truth. When you write code for other programmers. Other programmers read your code. Your computer doesn't give a shit about your code. Your computer cares about the compiled code. Your code gets converted into something that your computer will run. That's the argument for make your code nice and clean and let the compiler do all the optimization. When you hit run, your program gets compiled and then runs. Back in my day, when you were writing code in something like IntelliJ, you would have to hit compile, then you would hit run, but now it's one shot it. the compiler will turn the set of instructions that are actually run on the computer into as if it was written iteratively, because it's faster. In Java does that. That's called tail end recursion optimization. Other programming languages don't do that. There's varying philosophies as to why it's good and why it's bad. In reality, this would be just as fast. In fact, chances are it would be compiled to more or less the same thing for what the computer is going to be doing. But the code is just nice. All right, but it doesn't recursive function have a sort of beauty to it yet when considering the call stack. So here's like the call stack example of if I called recursive factorial on 4, let's think about what the call stack's going to do. Well, we would have our main, whatever, it calls recursive factorial with the value 4, which calls value 3, which calls it on the value 2, and then 1, and then 0. And then we would start popping from that call stack every time we answered the question. So what is recursive factorial 0? Oh, it's 1. Pop. What's recursive factorial 1? Well, it's 1 times. Sorry, recursive factorial 0 is 1. I think I just said 0. Pardon me. It's 1 times 1, pop. 2 times 1, pop, and so on and so on. So you can think of the call frames here from previous topic. All right. Some observations. So this is what I was kind of like trying to reason about how best to explain a moment ago. But let's see how I have it written down here. So this is an observation to me. You don't need to rationalize how important this observation is right now. But I want you to notice something. Notice how recursive factorial 4 makes a call to recursive factorial 3. Okay? That's not shocking. If recursive factorial 5 was called, right, it would need to calculate recursive factorial 4. Right? In other words, to know the recursive factorial of any arbitrary number x, to answer it, we would have to answer every previous possible question, previous like less than x value. So it's kind of like if I asked you what's recursive factorial 10, and then immediately after I asked what's recursive factorial 5, you might feel kind of annoyed because you're like, well, I kind of did just answer that. But I just kind of obliterated the answer in calculating the bigger one. But I did just answer it, because I would have needed to know what recursive factorial 5 was in order to know what 10 was. So that's kind of a funny thing. And also notice the relationship between the stack abstract data type and the call stack, which I was hitting in the previous topic, but hopefully it's kind of clear at this point. Instead of pushing data onto the stack, we're pushing these call frames. The call frames are this bookkeeping for our method calls or function calls, whatever we're dealing with. Anything you do with iteration, you can do with recursion. Anything you can do with recursion, you can do iteratively. They're two sides of the same coin, let's say. One is not intrinsically more powerful than the other. It's not. They're just, anything you do recursively, you could do iteratively. But this goes to the question you just asked. Just because you can doesn't mean you should, because at least for how these computers are designed, creating those call stacks, creating the call frames, pushing them on the stack, all that bookkeeping, popping from the stack, that's a lot of extra work. But programming languages like Java, for example, will optimize it so it actually doesn't make a bit of a difference. If you're using a programming language that doesn't do tail-end recursion optimization, you've got that trade-off of code readability versus speed. Not too long ago, I better stop talking now. All right, well, we'll stop there.